In this lecture, we prove a convergence criterion for the Jacobi method that one uses to generate a sequence of approximations to the solution of a system of linear equations given by the matrix equation A times x equals b, where A is a real-valued n by n matrix, x is a vector of n unknowns, and b is a vector in n-dimensional real space. The Jacobi method works by first transforming the matrix equation A times x equals b into an equivalent matrix equation of the form x equals c times x plus b star. C, like A, is a real-valued n by n matrix, and b star, like b, is a real-valued n-dimensional vector. We suppose that S is the unique vector solution of the matrix equation. And so the vector S should be equal to c times S plus b star, so that S is a fixed point of the Jacobi method. Let uppercase y sub m be the estimate for S obtained at the mth iteration of the Jacobi recursion. Then the Jacobi method's next estimate, y sub m plus 1, is equal to c times y sub m plus b star. We will prove the following convergence criterion for the Jacobi method. Suppose that for every row I of C, the sum of the absolute values of all the entries C sub ij is less than 1. This condition on the matrix C can occur when the matrix A is a strictly diagonally dominant matrix. Then the sequence of estimates y sub m will converge to the solution vector S as m tends to infinity. By convergence of y sub m to S, we mean that the maximum over all I of the absolute value of the difference between the ith component lowercase s sub I of uppercase S and the ith component lowercase y sub I of uppercase y sub m tends to 0 as m tends to infinity. Let X be a general vector in n-dimensional real space. The ith component of c times x equals the sum of the product of c sub ij and x sub j from j equals 1 to n, or c sub i1 times x sub 1 plus c sub i2 times x sub 2 and so on, up to c sub in times x sub n. Selon l'inégalité triangulaire, or according to the triangle inequality, the absolute value of the sum of all the terms is less than or equal to the sum of the individual absolute values of the different terms. Since we can split up the absolute values between factors of a product, we get this inequality. We denote the maximum absolute value of all the components of the vector x by this notation. This quantity is called the infinity norm or the max norm of the vector x. We'll refer to it in this lecture plainly as the norm of x. By definition of the norm of x, each x sub I absolute value is less than or equal to the norm of x. So the absolute value of the ith component of c times x is less than or equal to the sum from j equals 1 to n of the absolute values of the c sub ij's times the norm of x. Now this time, suppose that out of all these sums within the matrix C, we pick the row with the maximum sum of the absolute values of its entries. Since this quantity inside the absolute value is the ith component of c times x, the absolute value of the ith component of c times x is less than or equal to this maximum sum times the norm of x. This maximum sum of absolute values is called the norm of the matrix C. It is also referred to as the norm induced by the infinity norm of the vector x. We denote the norm of C using the same notation for the norm of x, taking care to remember how we are defining the norm of a matrix versus the norm of a vector. We take the maximum of the absolute values of all the components of c times x, giving us the norm of c times x. So the norm of c times x will be less than or equal to the norm of c times the norm of x. Since the theorem supposes that each of these sums is less than 1, and C has a finite number of rows, the norm of C will be less than some constant k, which is less than 1. And so the norm of c times x will be less than or equal to k times the norm of x. We define the error vector uppercase E sub m as the solution vector s minus the estimate y sub m, so that E sub m plus 1 equals s minus y sub m plus 1. Since s is a fixed point of the Jacobi recursion, s equals c times s plus b star. From the recursion, y sub m plus 1 equals c times y sub m plus b star. B star cancels out, so that E sub m plus 1 equals c times s minus y sub m. S minus y sub m is E sub m, so that E sub m plus 1 is c times V sub m. Applying this inequality, the norm of E sub m plus 1 is less than or equal to the norm of c times the norm of E sub m, which in turn is less than or equal to k times the norm of E sub m. Hence, we can compare the sequence of the norms of the E sub m's to a geometric sequence. This geometric sequence has a non-negative common ratio k, which is less than 1. Such a geometric sequence will tend to 0 as m tends to infinity. Therefore, the sequence of E sub m's will also tend to the 0 vector, so that the sequence of vector estimates y sub m that are generated by the Jacobi method will tend to the exact vector solution as m tends to infinity.